He has ongoing studies of risk assessment, particularly with respect to the criminal justice system. He'll be talking today about making fair decisions with algorithms. Thank you, Sam.
All right, hi everyone. Thanks for coming out and having me this morning. So this is some work that I've been doing with colleagues at Stanford, Emma Pearson and Shara Goel, colleague at Berkeley, Avi Feller, and colleague at University of Chicago, Aziz Haq. So we've been looking at this question of how can we make fair decisions with algorithms. And how this kind of started is we were looking at how to identify bias in algorithmic decisions. And our background is actually looking at bias in human decisions. So I started out looking at whether police officers are discriminating in who they decide to search at a traffic stop. And we thought, well, algorithmic decisions and human decisions there are a lot of similarities, right? In the end, you've got to decide who you're going to search. And whether it's an algorithm making that decision or a human making that decision, maybe there's not that big a difference. So maybe we can apply some of the things we've learned testing for bias in human decisions to bias in algorithmic decisions. And the case study I'll talk about during this talk looks at pre-trial decision making, right? So if you get arrested, you go before a judge, and the judge has to decide, should you be detained before your trial or should you be released? And their mandate is to ensure public safety and that you'll appear in court while releasing as many defendants as possible. And we want to know, do judges exhibit racial bias in these decisions? So there's a few ways we might go about this. And in this talk, I'll be using data from Broward County that was made available by this ProPublica study that you've heard about already. The first test is known as the benchmark test, and we just compare the rates of detention between comparable groups. So a typical statement here might be like controlling for age and the number of prior convictions. Black defendants are 3 percentage points more likely to be detained than white defendants. Right? And we might argue that this is indicative of discrimination in the choice to detain black defendants. But there are some obvious problems with the benchmark test. And the main one is the omitted variables problem. Right? So decision makers, judges, almost always have more information about the defendant than we have as researchers. So the judge can talk to the defendant, and face-to-face decisions, right? We don't observe as researchers everything that the judge observes. So the disparities in detention rates could be caused by these variables that we don't observe. Judges might say, look, the reason I made this decision wasn't because of their race, it was because I'm really worried about violent offending, and there were different violent backgrounds of different defendants. So improved test took this insight, as developed by the economist Gary Becker, and said, well, judges are trying to achieve something, right? They're trying to achieve, they're trying to release the defendants who are unlikely to commit a crime before their trial. And so the outcome test says, why don't we just look at the reoffending rates just for the defendants that judges release? So we let judges release different groups of defendants at different rates, and we just look at who reoffends among the people we release. And if one group reoffends less often than another, it suggests that judges are holding that group to a higher standard and therefore discriminating against them. So again, we can look at data from Broward County. We see that released black defendants reoffend 47% of the time, whereas released white defendants reoffend 33% of the time. So in fact, the outcome test in this case finds that judges are discriminating against whites. Now there's a problem with the outcome test, and to understand it, we need to think about risk distributions. So this is the distribution of the probability of reoffending given all the information used by the judge. So you can imagine a judge sitting in the courtroom, and they might see 100 defendants over the course of a week. Some of those defendants are going to have no previous convictions. They've come in for something minor, and there's a very low chance they're going to reoffend, in which case they'll be on the left-hand side of this distribution. Other defendants will have long rap sheets, and for whatever reason we believe they're a higher chance of reoffending, so they're going to be on the right-hand side of this distribution. And over the course of a week, all these defendants are going to form this nice distribution where like the majority are somewhat low risk, and there's this long tail of high risk defendants. Now risk distributions can have different means, right? So the mean of the distribution is the average reoffending rate for all defendants. So if we just released everyone, the mean of this distribution tells us what proportion of those defendants will reoffend. So a risk distribution with a higher mean means that that group reoffends more often on average. Distributions can also have different variances. Right? This says that it's harder to determine who's high risk and who's low risk for certain groups. So in this case, the red distribution is more clustered towards the mean. All the defendants in the red group look kind of similar. This might be the case if it's the first time in court, we have very little information on this defendant. And so it's hard to distinguish who's going to be high risk and who's going to be low risk. Whereas the blue distribution has more mass towards 0, those are the people who are very unlikely to reoffend, and towards 1, the people who are very high risk. And so it's easier to distinguish between those different defendants. Now, the problem with the outcome test, which we saw suggested discrimination against whites in Broward County, is that let's say the judge decides to apply a threshold that's group neutral, right? Whether you're in the red group or the blue group, if there's a less than 20% chance you'll reoffend, you'll be released. Otherwise, you'll be detained. Now let's see, what is the reoffending rate of these released defendants? If we look at the risk distributions, the reoffending rate is the average within this shaded section here. So it's the average conditional on being below the threshold. And because there's this mass of blue defendants really close to 0, the mean conditional on being below that threshold is higher for the red group, lower for the blue group. So the outcome test suggests discrimination against blue because the outcome test compares reoffending rates. Why does it do that? Because there's many extremely low risk blue individuals. But by construction, all defendants have faced the same threshold, so there's actually no discrimination in this case. This problem is known as the problem of infra-marginality. Right? People who are very low risk will be released whether or not judges are biased. And infra-marginal statistics, such as the reoffense rate, average over this entire section of the risk distribution. And therefore, they're affected by the relative number of very low risk defendants in different groups. Because this discrimination occurs on the margin when someone who wouldn't have otherwise been detained is detained because of their race, we want to determine that threshold. We want to know what is that threshold for different groups. And this is the general problem with identifying bias in human decisions. Prejudice manifests itself as different thresholds, but in human decisions, we can't measure those thresholds directly. Right? We don't observe all the variables that judges use to make their decisions, and the marginal reoffending rate, that is the threshold, isn't the same as the average reoffending rate, which we observe. So now let's move on to making decisions with algorithms. Right, so in many jurisdictions across the US, these decisions on who to release and who to detain are informed by risk assessments. Right? This is a machine-learned mapping from defendant features, such as the age at current arrest, whether the offense that they're charged with is violent, etc., to some risk score. Right? And the risk score attempts to predict whether a defendant will commit, say, a new violent crime. And there are promises here. So this paper from John Kleinberg et al. In the Quarterly Journal of Economics suggests that crime could be reduced by 25% in New York City if they switch to using a risk assessment with no increase in jailing rates, or jail populations could be reduced by 42% with no increase in crime rates. And this can also happen while reducing the percentage of African Americans and Hispanics in jail. So there's some promises here, but there's also concerns, right? So as we've seen, ProPublica investigated Broward County. They found that the false positive rates that a certain risk assessment tool produced were higher for black defendants than for white defendants. Right? So of defendants who didn't go on to reoffend, black defendants were more likely to be rated as high risk. So I'm going to go over 8 potential fairness concerns in using algorithms to make decisions. And again, I'll be talking about this case of pretrial risk assessment. The first is miscalibration. Right? So are we systematically overestimating a group's risk? The second is redlining. We could discriminate by ignoring relevant information about certain groups. There's sample bias, and this is the situation with the potholes, for example, where the training data that we use is not representative of the problem that we actually care about. There's label bias, when there's measurement error in the training labels. For example, we measure arrest, but what we actually care about is crime. There's subgroup validity, which is when features are differentially predictive for different groups. There's use of protected characteristics, right, including race and gender in the model, is a big fairness concern. There's the disparate impact that these models can produce, which is when groups are detained at different rates or rated high risk at different rates. And there are disparate error rates, as Moritz talked about, when the false positive rates or perhaps the false negative rates differ between groups. I'm going to group these fairness concerns into 2 groups. The first, on the left here, can be fixed without the need to sacrifice efficiency. So addressing these fairness concerns isn't in tension with the goals of the decision maker. So these are in some sense easier, perhaps not easier to address in practice, but easier to convince the decision maker that they should be addressing these problems. The second set of concerns present a fairness efficiency trade-off. Right? And these are the trade-offs that have been discussed all morning. What I'm also going to argue is that they present a fairness trade-off. That is, addressing these concerns actually introduces different unfairness into the decision-making process. So I'll go through these in more detail one by one. So calibration says that conditional on a risk score, groups should reoffend at equal rates. And this is the way that criminologists assess the fairness of these risk assessment tools, which they've been building for sort of 15 years or so. And so we can see if we plot, this is for Compass again, we plot the risk score from 1 to 10, and we look at within each bucket what proportion of black and white defendants reoffend. And we can see that the lines overlap, and Compass would, Northpoint, the developer of Compass, would use this result as evidence that their tool is unbiased. Now, if you look at Broward County, something really interesting comes out, is that there is actually miscalibration by gender. So again, we plot the risk score and we look at the recidivism rate, and we see that the risk of women is systematically overestimated by the Compass algorithm. Women with a risk score of a 5 reoffend about as often as men with a risk score of a 3. This seems like strong evidence of bias against women in this risk assessment tool, which is currently being used in Florida. The reason why addressing calibration isn't in tension with the utility of the tool is that if we see a picture like this, we're going to over-detain women relative to men. And as a result, because empirically men are more risky, there'll be more crime, or we'll have to detain more people to achieve the same crime level. So fixing this miscalibration will improve the effectiveness of our tool. But as I said, criminologists believe that calibration is sufficient for fairness, or some of them do. And often in computer science, there's also a group that believes that calibration is sufficient. But we argue that it's not. And the reason for this is that there are many possible risk scores that are calibrated, right, but that aren't the best estimate of risk. So, most logistic regressions that you fit on some problem will end up being calibrated. But because there's so many, a biased decision maker could pick and choose the one that achieves, that at most advantages their favored group or most disadvantages their unfavored group, right? Yeah.
So to this example with men and women, there might not be any data of gender that you can use for calibrations, right? So and you're not allowed to introduce the gender as a criteria.
Yeah, I'll cover that. But you're exactly right. This is a tension between the law as it stands and this concern. Yeah. And I should point out that this could happen with a biased decision maker who's explicitly discriminating, but it could also just be oversight, right? The designer ignores some feature that could significantly improve the performance for one group, but just fails to include it. The reason we use the term redlining for this is by analogy to lending discrimination, right? Where banks ignored the individual creditworthiness of minority applicants or applicants in minority neighborhoods. And such a policy could be calibrated in the sense that those minority neighborhoods might have had higher average default risk. So the bank can say, well, we're not lending to that group because of their race, they're lower risk on average. But the problem is that they've ignored the qualifications that any individual borrower in those neighborhoods could have. Right? So this redlining problem is when information is ignored in such a way to discriminate. To give an example of how it works, imagine this is the world. There's white defendants and black defendants. And the only thing that affects whether they're likely to reoffend is the number of previous convictions they have. Right? So with 0 previous convictions, defendants reoffend 5% of the time, 1 to 2 convictions, 20% of the time, 3 or more convictions, 40% of the time. And both groups reoffend on average 20% of the time. Now, a possible calibrated risk score is first for black defendants, we put them into 3 buckets based on the number of previous convictions. But for white defendants, we ignore the number of previous convictions and just put everyone in the middle bucket, right? Because on average, white defendants reoffend 20% of the time, which is just as often as black defendants in the second bucket reoffend. So this is a calibrated rule because everyone in that second bucket, whether white or black, reoffends 20% of the time. But now we can apply a 25% threshold. So we say we'll detain anyone with a greater than 25% chance of reoffending. We only end up detaining the third bucket. Right? We only end up detaining black defendants. So we've got a calibrated risk score. We've got a uniform threshold that doesn't depend on the race of the defendant, and yet we're only detaining black defendants in this example. And this points to a general way to discriminate if you're a bad actor, where you can just add noise to the risk scores of a favorite group. So you train your model, and let's say you want to favor white defendants, and initially they have this sort of risk distribution here, where there's like some defendants who are pretty high risk and quite a few that have the features indicating they're low risk. And you just add noise to that model, right? And what adding noise does is it blurs the distinction between high risk and low risk defendants. And what that looks like in risk distributions is the mass moves towards the mean, right? Everyone starts looking more and more similar. And you just keep adding noise until the vast majority of the group you're trying to favor is below the threshold. And if we look at the calibration plot here, the risk score and the actual probability of reoffending, both algorithms, the black original scores and the red doctored scores, both calibrated, and yet now you're detaining no white defendants. So in the lending example, we were ignoring information about the disfavored group. In this bail example, we ignore information about the favored group, but the mechanism is the same. So calibration is necessary, but not sufficient for fairness. And the reason I say it's necessary is that without calibration, it's unclear what it means to have a risk score. So if you ask me how risky is this defendant, and I say there are 2, and you say, what does that mean? And I say, well, if they're male, it means there's a 50% chance they'll reoffend. If they're female, it means there's a 20% chance they'll reoffend. You can see how 2 loses its meaning in that case as a risk score.
Can I ask a question on
Sure.
this? Isn't it also true for the binary decision in the end? Like once you threshold, the binary classifier resulting from that loses calibration anyway?
It loses, like the precisions won't be equal.
The precisions won't be equal, so
Right.
the argument you just described, you could mount that against the resulting binary predictor, right?
Well, the binary predictor is going to depend on who's far away from the margin, right? So if there happens to be a lot more murderers in one sample, then there are going to be a lot of obviously high-risk people, which is going to drive up your precision for that group without saying anything about how you're treating defendants on the margin. And so it's equalizing that precision is less important because it depends on those defendants that are further away from the margin.
But now, you could have a score with 10 values or 5 values or 3 values. I mean, there's no...
Yeah, so
distinction here,
right, and that's a sort of subset of this. By decreasing the number of values, you're obscuring information that could be used to make distinctions between defendants.
Which makes this not necessary is if you are allowed to look at the attribute, the sensitive attribute at decision time.
So looking at the sensitive attribute decision time versus adding it to the model and therefore ensuring it's calibrated are like 2 sides of the same coin. So because of this, you can't determine fairness of an algorithm without inspecting the features used, right? Because we could have, the designer could have excluded some feature that in order to discriminate. And one way to avoid this problem is to use all the available features, which also produces the most accurate algorithm, which is why requiring calibration, avoiding redlining is in the interests of the decision maker. So a third fairness concern is sample bias. Right, so the data set that we're training on is sampled from the population in a biased way. So an example of this might be predictive policing algorithms that are trained on policing from historical data where over-policing was present in minority neighborhoods. And as a result, they're going to predict that crime will continue to occur in the neighborhoods where policing discovered that crime initially. Again, this is in the interests of the decision maker to address because the city wants to limit crime. And so knowing that there are crime in areas where we didn't sample from is going to improve our results on that metric. So again, addressing sample bias is in the interest of the decision maker. There's also a label bias, right? So again, over-policing in minority neighborhoods might mean that if a white and black person both commit an offense, the black person is more likely to be arrested and appear as a positive in our data, right? Because we observe arrests, whereas what we actually want to predict is crimes. And this is a real problem, right? So if you're training a risk assessment on drug arrests, you're going to systematically overestimate the risk of minority defendants. What criminologists use to address this is that they use violent crime as their outcome. And that's because they find no evidence that the probability of being arrested given you've committed a crime is greater for one race or another. Right, so arrested for a violent crime is the least biased outcome that we have available to us. Finally, there's subgroup validity. Yeah, sorry.
So in this case, I mean, even if you don't make an arrest and people are not policing certain neighborhoods, you still know whether a crime has occurred in that or not.
It's usually quite hard, right? So you could use.
So like somebody is robbed, then they will report that.
Yeah. So
it naturally move to policing those areas more where the crime is.
Right. So things like robberies, it's much easier to detect where crime is occurring. But things like drug crimes, there's probably a lot of drug crimes happening in Berkeley dorms right now that we'll never find out about. And generally measuring the true crime rate is a challenging problem, right? The reason we use violent crime is that it's easier to determine, because of victim reports, it's easier to determine the true crime rate. So finally, there's subgroup validity, right? So I talked about bias in the labels and thing we're trying to predict, but there's also bias in the input features, right? So if we use drug arrests in our model, and we know that drug arrests are biased in the sense that conditional on committing a drug crime, minorities are more likely to be arrested, we'd expect that using drug arrests would overestimate the risk of minority defendants. Right? And what we'll see if this is the case is miscalibration. But the advantage of bias, or the saving grace of bias in the input features, is that as long as the labels are unbiased, we can learn to correct these biases with the appropriate interactions. So an example outside of criminal justice might be that we're trying to predict who will succeed in a job. And we notice that men who have extended periods of joblessness, perhaps that's a negative predictor of future job performance. Whereas women who have, say, a year off are often just on maternity leave and it has no bearing on whether they'll be successful in the job. Without knowing whether the applicant is a man or a woman, we can't learn to correct that bias, but if we know, we can correct it. Again, this is the picture we see in Broward County, and if we just add gender to this model, we're going to correct this bias and stop detaining women at higher rates. So now look at the second set of fairness concerns that present this fairness trade-off. The first is the use of predicted characteristics, and we've talked about this already today. It's legally questionable under the current law. So adding gender to this model to fix this miscalibration is probably illegal under current understanding of anti-classification laws. But as Corbett et al. In the University of Pennsylvania Law Review discussed, there may be cases where allowing an algorithm to consider protected class can actually make outcomes fairer. This might require a doctrinal shift, as in many cases, considering protected status in a decision is presumptively a legal harm. Right, so we know that in theory, there are lots of situations where adding a predicted characteristic to the model actually makes it more fair, but currently the legal understanding is that that is not allowed. Another concern we might have is about disparate impact, right? Which is when one group is detained more often than another. And this is often encoded in computer science papers as statistical parity, right? The requirements that all groups be detained at equal rates, or that the decision should be independent of protected characteristics. If we look at Broward County, we see that 57% of black defendants was rated as high risk versus 33% of white defendants. So there's disparate impact in the COMPAS scores in Broward County. But there's a problem with statistical parity as a measure of fairness. Right? It's analogous to the benchmark test, which I talked about at the start of the talk. Right? The differences in detention rates might reflect differences in risk, and we can't see that just by comparing these scores. Right? We can partially mitigate it with controls, which some authors refer to as conditional statistical parity. So you might say that conditional on the age of the defendant and the number of previous convictions, we shouldn't see different detention rates among different groups. But there's always the question of what do we control for? There's also disparate error rates, right? So this says that false positive rates should be equal for all groups. And false positive rate, of course, is the number of detained defendants who wouldn't have gone on to reoffend divided by the number of defendants who wouldn't have gone on to reoffend. And this is ProPublica's evidence of bias in COMPAS, is that this ratio was higher for black defendants than white defendants. So we can look again in Broward County, 42% of black defendants who didn't go on to reoffend were rated high risk, whereas 22% of white defendants who didn't go on to reoffend were rated high risk. So where did these disparities come from? And where they come from is that the risk distributions for black and white defendants have different shapes, right? So in blue here is the risk distribution for white defendants, and in red is the risk distribution for black defendants. And once you choose a threshold in this space, so you can decide whether you want to be very strict and detain almost everyone, or you can decide if you want to be lenient. But once you choose a threshold, everything else is determined, right? The detention rates and how they differ, the false positive rates and how they differ. The optimal policy is a single threshold in the sense that detaining the riskiest X defendants means that you'll detain the fewest number of defendants for a given acceptable crime rate, or alternatively, you'll minimize crime for a given number of defendants detained. But even if average recidivism rates are equal, there could still be differences in the shapes of these distributions. So the mean of these two distributions is the same. So on average, both groups reoffend equally often. But once we apply a threshold, anything goes. There could be disparate detention rates, there could be disparate false positive rates. What we show in our paper, and Marissa's talked about this, is that the optimal policy that equalizes detention rates or false positive rates uses race-specific thresholds. Right? And then this means that there's a tension between individual fairness, right, that all defendants should be held to the same standard, and group fairness, that we should try to equalize detention rates or false positive rates. So what this looks like might be something like this, where we choose to detain black defendants if they score greater than a 7 on the risk scale, but we choose to detain white defendants if they score greater than a 5. And what's the result of this? And we can look again at the Broward County to see Broward County data to see what happens here. So first of all, there are some low-risk defendants that were detained because of their race. Right? These are the white defendants here who score a 5 or a 6. They wouldn't have been detained if they were black. And if we equalize, say, false positive rates in the Broward County data, those defendants will make up 14% of the total number of defendants that we detain. Right? And these defendants will bring a 14th Amendment case alleging that their equal protection rights have been abridged because, as I say, they wouldn't have been detained had they been a member of a different race. But there's the other side of it, which is that because we're detaining low-risk defendants while releasing some relatively higher-risk defendants, there's going to be an increase in violent crime committed by released defendants. And because we know that crime generally occurs within communities as opposed to between communities, this crime will be concentrated in minority neighborhoods, and the victims will also bring a 14th Amendment case. Right? So they say, you released a defendant into my neighborhood who you wouldn't have released into a white neighborhood, and as a result, I was victimized. Because of this, as a statistical likelihood, some number of those defendants will go on to commit crimes. So therefore, my 14th Amendment rights have been violated. So there's costs here to fairness from both sides, both the people who are newly detained and the increase in violent crime resulted from the people who are released. So we can see analogies between these measures of fairness and the tests for discrimination that I talked about at the start of the talk. Right? So as measures of fairness, disparate impact and disparate error rates face the same problems as their related tests for discrimination and human decisions. Right? We've already seen that disparate impact is similar to the benchmark test in that both compare rates of detention, but ignore the possibility that different risks might necessitate different detention rates. Disparate error rates is similar to the outcome test in that both compare infra-marginal statistics. Right? Both compare statistics that include not only defendants close to the margin where discrimination might occur, but also defendants far from the margin where the decision wouldn't be changed either way. To flesh that out a bit, consider this toy example. Right? We have some defendants in a blue group, and some risk assessment algorithm has scored these defendants. And it's a calibrated algorithm in the sense that if this defendant has a 0.4% chance of reoffending, 40% of the time they'll reoffend. And we have this orange group that has a higher mean. They reoffend more often on average. And we decide to detain defendants if there's a greater than 50% chance they'll reoffend. We can look at false positive rates. We see that this group has a 25% false positive rate, whereas this group has a 42% false positive rate. This is roughly the picture that ProPublica saw when they studied Broward County. But what happens if before they came to study Broward County, the police in that county strictly enforced, say, jaywalking laws or some other minor law in the district? And as a result, there are a lot more low-risk defendants of the orange group detained. So a lot more low-risk defendants came into the system. Right? And because they've only been caught jaywalking, there's a very low chance they'll reoffend. And so we don't detain any of them. They just get released. Now let's look at what's happened to the false positive rates. The introduction of these low-risk defendants has reduced the false positive rate to 26%. And so if ProPublica came and studied this version of Broward County, where the cops were being a bit overzealous on the orange group, they would find no discrimination according to their measure. Right, so let's see what's happened. The risk assessment algorithm hasn't changed, right? Everyone's scores are still the same. No defendant's decision has changed, right? Everyone to the right of the threshold is still to the right of the threshold. Everyone to the left of the threshold is still to the left of the threshold. And yet, the false positive rates tell totally different stories. In this picture, we'd find discrimination against the orange group, whereas in this picture, we don't see any discrimination according to the false positive rate metric. This is the exact problem that we saw in the outcome test, the problem of infra-marginality. And the problem is that false positive rates are confounded as a measure of discrimination by the distribution of obviously high risk and obviously low risk defendants. So in this example, we added a lot of obviously low risk defendants, and we could change the false positive rates without changing anyone's decision. Now in the problem of studying human decisions, we don't have a way of measuring the threshold, right? But in algorithmic decisions, we can directly observe and change the threshold. So this is our prescription for making fair decisions with algorithms. Ensure the following concerns are addressed. So we want to make sure that there's no miscalibration, that there's no redlining, that features aren't being ignored because in order to discriminate, that there's no sample bias, that we've adequately addressed label bias, and that we've addressed subgroup validity problems. And a lot of these concerns require transparency. So at least a government auditor or someone like that has to be able to look into the algorithm and how it was constructed, the training set that was used to construct it, in order to determine that these fairness concerns have been addressed. And once we have a risk assessment that satisfies those concerns, then we choose a single threshold to make our decision. So there are some limitations to this approach. Some decisions, such as college admissions, don't operate on individuals, they apply to groups. So when we're admitting students to college, we don't want to pick just the 100 students that are most likely to graduate. Right, we want to pick the class of 100 that is going to be most successful. And there's interactions between students in that case. Our analysis also doesn't consider the long-term equilibrium. So Moritz talked about how you might be willing to trade off some utility now to achieve a better long-term outcome. In computer science, people often talk about exploration versus exploitation, where maybe we don't have enough information about one group, so we change how we're releasing people to explore better how they would perform if we release them. And our analysis also doesn't consider the possibility that some defendants could be more costly to detain. So for example, a single mother with dependent children might be more costly to society and to her to detain her than detaining a young man. So that's my talk for today. Thanks very much, and take questions. Yeah.
So did I understand you right that in the compass example, these false positive and false negative rates weren't a good measure?
Yeah, the reason for that is because they depend both on what's happening around where the decisions are made. So there are always going to be defendants where it's like it's a tough decision whether they should be detained or not, right? And that's where race might tip the balance, for example. Whereas there's going to be defendants where it's very easy to make the decision, whether it's very obvious that they're not going to reoffend again, or it's very obvious that they're high risk and need to be detained. False positive rates and detention rates average over both groups. And so what's happening among the really high risk and really low risk defendants can change our assessment of what's happening where the hard decisions are, where race can tip the balance. And that's what people who study human decisions have realized in their test for discrimination. And we're trying to bring that insight into determining whether algorithms are fair. Yeah.
How robust are these thresholds? So like,
say more.
if, for example, you you have some kind of adversarial system where you give someone a classifier and then they have to apply it. They want to be as able as possible to discriminate with regards to something, and then they don't really care about fairness, but you want to make sure that your classifier is robust so that whatever you give them, even if they play around with the thresholding a little bit, they can't make it too unfair.
Right, so this is the example maybe where judges get given, as is the case now, judges get given a risk score, right? So this defendant is 7, but in the end, they still make the decision. So you can imagine them deviating a long way from the policy suggested by the algorithm. I think we don't really have evidence on what judges are doing in that case. The strict rule would just be like, get judges out of the way because they might add more bias than they actually solve if we're concerned about them fudging with the thresholds. But yeah, I don't think we know exactly how judges are using these scores.
Like for the thresholds that you found, that you said that like having two different thresholds.
Right.
Is that approach more robust, less robust? Do you guys have any insight? Just marginal changes in the threshold.
I guess in any situation, if you let the decision maker mess with the threshold, it's going to deviate from what I've discussed, right? So it's going to be, presumably, it's either going to result in disparities in false positive rates or something, or it's going to sacrifice some efficiency. Yeah.
So in this case, it seems like once the judges are made aware of the potential bias in the risk scores predicted by Compass, maybe they can actually unbias the decision. And be like, okay, this is probably like, for the same score I would have done this, but let me now revert back.
Right, so it might be an apocryphal story, but I've heard that one particular dogged activist is going around to judges but saying, mentally take 2 points off whenever you have a woman in your courtroom, right? And you can see why, because the gap here is 2 points. And so taking that 2 points off for women means that now you're actually comparing real risk. And yeah, again, that's good in the sense that it would stop us from discriminating against women. But I think
analysis might help decision makers unbiased decisions.
Right. I think if judges explicitly said, I'm taking 2 points off for women, that's when you get into the realm of, well, now you're using a particular characteristic to make decisions, and under current understanding of discrimination law, that might be illegal. So even though there are these, there's this miscalibration, addressing it might be illegal. And I think there's definitely room for a court case to correct that. Yeah.
Right. Let me make another point. So basically, in some sense, calibrating a model often boils down to finding features that redundantly encode the sensitive attribute, like finding a proxy for it, like basically.
Oh, if you be like here, we could use hair length to calibrate.
Yeah. Like features until this goes away.
Right. Yeah.
And so the only thing you've done is you've built a proxy for the sensitive attribute, which means your model can calibrate itself, and this problem goes away. But in some sense, as far as the law is concerned, if all you did was you found a proxy,
yep,
and using that, it's just as bad.
Well, yeah. Well, I'm actually advocating for using the thing itself here, because that's how we can ensure that the algorithm is calibrated. Right? Look, using gender.
Right.
Right. Like, I mean, we could use proxies to like maybe try and get around the law, but.
I completely agree. That's essentially what you're advocating. But
yeah.
That means that also is in sort of tension with.
Absolutely. Yeah, and I think like using an example like this in a court case is where you might get a decision finding that actually using predicted characteristics can improve fairness.
Okay, so maybe we should, let's thank Sam.